some time to grab a drink or so. Start in a minute or two, and I'll start with the official intro then, so you still have some time. All right. Then first of all, I want to welcome everybody who has joined today for this webinar today. And the webinar will be on accurate electronic properties of molecules and materials from the GW approach. And I just wanted to introduce what we will talk about today. So we have two talks. We have the first talk from James Green on an overview of methods for electronic excited states within FHI-aims. And James has obtained his PhD at the University of Leeds in 2018, then did a 3-year postdoc at the Italian National Research Council in Naples, and had an Alexander von Humboldt Fellow afterwards until 2024 in Frankfurt, Germany, and has been with MS1P since last year. The second talk today will be by Dorothea Golze on charge excitations from the GW methods. And Dorothea has obtained her PhD in 2016 at the University of Zurich in the group of Professor Jörg Hütter, and has then done a postdoc with Patrick Rinke at the Aalto University in Finland. And since 2021, she has been a junior group leader at the Technical University of Dresden here in Germany. And her main research field is the development of highly accurate methods for theoretical spectroscopy of materials, and also their implementation for massively parallel execution on high-performance computing platforms. In addition to the two talks today, which will begin in a second, we also have a second day planned for this webinar. So this is day 2 tomorrow, where we'll have 2 hands-on and discussion sessions, one in Europe time in the morning at 9 a.m. CEST, as well as one later on at 4 p.m. CEST. Both of them will do essentially the same thing. So we will go through a hands-on tutorial on provided computing resources together. But this is also open to everyone for discussions if you have any questions on FHI-aims, the GW method, and so on. If you already signed up for these hands-on sessions, you should have gotten an email already with the credentials you need later on to sign onto the cluster. But again, more on this tomorrow. You still have time to sign up today at our webpage for the webinar in case you still want to take part in these hands-on sessions. And then what we'll do in the tutorial, which you might already know, is that we'll run through a tutorial on calculating charge excitations with the GW approach. So there will be both in core and valence electrons, both for molecules and solids. And all this with FHI-aims. So I hope to see a lot of you there. But then again, I would now hand over to James for the first talk of the session. So James, please go ahead.
Recording in progress.
Okay, so hopefully you can see my screen now. Yes.
Yeah,
Okay.
that works.
Perfect. Okay, thank you. So yeah, thank you for the introduction, Konstantin, and welcome everybody to this webinar. So my name is James Green, and I'm a software scientist at Molecular Simulations from First Principles, or MS1P, here in Germany. And yeah, in my talk, I'm going to first give a short introduction to FHI-aims, and as well how we at MS1P fit in with this. And then I'll go on to give a brief overview of different methods for electronic excited states in FHI-aims. So the first thing that I should say about FHI-aims is that it's really a community project, a community code. So there have been contributions from over 150 people in 20 years all over the world. And really, the code wouldn't exist as it is without these people. So yeah, thank you very much to everybody you see on the screen, plus potentially others as well. So how we're organized. So like I say, FHI-aims is a community-based software, community-based code. It's hosted on an open development platform on GitLab. So there, once you have access to the code, anybody can contribute. And really, new physics and new methods are constantly being added by different scientific groups around the world, as you saw on the previous slide. And then how MS1P fits in with this. So we are a German nonprofit society with 5 employees plus an executive board. And we're essentially here to support this FHI-aims community and the code. So we're responsible for licensing FHI-aims both to academia and to industry. And once you have a license for FHI-aims, you can register on the GitLab and have full access to the source code plus wiki pages and issues and things like this. And you can also download the code or release versions of the code at our website, or at the FHI-aims website. We're also responsible for help with code stability and integration. So when a scientific group adds one of these new methods, we help to try and integrate it with the existing FHI-aims software to ensure everything is still working correctly. And we also help fix bugs that come up during this process and otherwise as well. We also provide community support, and one of the main channels we have for the community is a FHI-aims Slack channel. So at the moment, this has around 1,000 people on it, and generally this is the first port of call. If someone has problems or questions with FHI-aims, they can post a question there, and generally either one of us at MS1P or someone else from the FHI-aims community will be on hand to help out. We also help with documentation, webinars such as this one, and tutorials such as the one that will be tomorrow. And as well, we collaborate with industry partners as well. So I mentioned the website on the previous slide, and this is where you can get the code. And you can also see a wide range of online tutorials that we have for FHI-aims. So at the moment, I think there's more than 30 tutorials, and these are constantly being added to, primarily by people who have developed new methods and want to explain to others how these methods work. And we at MS1P also add and edit some of these tutorials as well. And I'll mention some of these tutorials when I get onto the part of the talk about excited states. As well, on the website, you'll see at the moment a link to a preprint of the FHI-aims roadmap. And this is on arXiv and has more than 30 sections with over 200 authors, essentially describing the last 20 years of development of FHI-aims, plus where it will hopefully go in the future. And I'll touch on some chapters of this roadmap paper a little later on as well. We also have a YouTube channel, which maybe some people are watching on, where we also have introductory videos, tutorials, and recordings of this webinar series and other series we've run. Okay, so now that's kind of a quick overview of the infrastructure of FHI-aims and how MS1P fits in with that. So now onto the code itself, and I'll just briefly describe essentially the philosophy and the design principles that went into creating FHI-aims. So from the outset, the vision was to create a software that is capable of conducting quantum mechanics-based simulations of real complex molecules and materials and their properties without a priori precision and accuracy limitations. And there's kind of three key points to this. So the code should be versatile, so capable of simulating both non-periodic or molecular systems on the same footing as periodic or material systems. It should also be precise and accurate, both for all electron density functional theory and correlated methods beyond DFT as well. And finally, it should be scalable from laptops to large HPCs with thousands of compute nodes or thousands of CPUs, and from tens to thousands of atoms. And a key design choice that was made in trying to fulfill these aims was to use numeric atom-centered basis functions. So as many people everybody who's done some kind of quantum mechanics simulations before knows, we generally represent a wave function, in this case electronic wave function, as a basis set expansion in terms of basis functions phi I. Now in many molecular electronic structure codes, Gaussian basis set is chosen, and for periodic codes, quite often plane waves are chosen. So in FHI-aims, instead, the choices use numeric atom-centered orbitals. And so this is how they are represented in terms of a spherical harmonic YLM plus this U of R, which is a numerically tabulated radial function. So this numerically tabulated bit is where this name NAO comes from. And because they're numerically tabulated, they can have a flexible shape. So in particular, we can account for these little wiggles near the nucleus. And they're capable of describing an all-electron description as well. So we fulfill our criteria of being accurate. As well, we can apply a cutoff potential. So that's shown by this black line here, which ensures our radial function is 0 beyond this dotted line here. And this makes the NAOs localizable, which means that they can scale on the order n for most of the computationally expensive steps of the calculation, which makes it scalable. So the second point. And as well, these NAOs can be used for both non-periodic and periodic calculations, so satisfying the final point from the previous slide. And we have a basis set library available with these NAOs in the FHI-aims code, ranging from fast qualitative calculations to converged calculations. And really, we only need a rather compact basis set for converged calculations as well, which is quite nice. Okay, so now that this is the brief philosophy of FHI-aims, I'll spend the next 12 minutes or so just giving an overview of different methods for electronic excited states in FHI-aims. So when we think of electronic excited states, we can broadly categorize them in two ways. So we have charged excitations, where an electron can go from a core or valence state to the vacuum, and we can get ionization potentials or binding energies. And we can also have neutral excitations, where we promote an electron from a valence state to an empty state. And we have a few different methods in FHI-aims to treat both of these scenarios. So firstly, we have GW, which is for charged excitations, both in molecular and periodic systems. We have the Bethe-Salpeter equation and different flavors of time-dependent density functional theory, so linear response and real-time, to describe neutral excitations. And we also have the delta SCF and equation of motion coupled cluster methods, which can describe either charged or neutral excitations. And so in the next slides, I'll just give a brief overview of each of these methods. So first, molecular or non-periodic GW. I won't go into very much detail at all about this, since it's going to be covered in much greater detail by Dorothea, as her group is one of the main developers of the GW method in FHI-aims. Just to say, the central idea behind GW is computation of this self-energy sigma, which accounts for the exchange and correlation energy of an electron or hole with surrounding electrons in a multi-electron system. So this is a frequency integration of the Green's function G multiplied by a screened Coulomb potential W. And so this is where this GW gets its name from. And with this, we can compute charged excitations from valence to deep core. And the implementation in FHI-aims can go to around 250 atoms, scaling to the 4th power. We have lots of different options for GW in FHI-aims. So there's different relativistic references, different flavors of GW, from the one-shot G0 W0, where a single GW calculation is done on top of a ground state DFT calculation, to various varieties of self-consistent GW. We also have different methods to do this frequency integration and different post-GW corrections that can be applied as well. And yeah, as well as Dorothea's talk, this will be covered in the tutorial tomorrow for those of you who've registered. In periodic GW, we just have one-shot G0 W0. And a general use case for this is to provide corrections or more accurate band gaps than DFT calculations. So in this figure here, you can see from this implementation paper from Jinggu Ren, whose group also has done a large portion of the implementation of GW in FHI-aims, a comparison between the FHI-aims calculation and a plane wave code, as well as a comparison to experimental band gaps for these materials, showing a good comparison. We also have specialized basis sets for periodic GW and FHI-aims, which will be covered in the tutorial tomorrow. And the method can scale up to around 100 atoms, as you can see in this figure from the roadmap paper, up to 81 atoms for zirconium dioxide unit cell in this case. Okay, so next to the neutral excitation. So the Bethe-Salpeter equation can be used for valence and core excitations. And the idea behind this is you do a DFT calculation from which you can get a screened Coulomb interaction with a random phase approximation. And then you perform a GW calculation to get quasiparticle energies, which are then fed into this BSE eigenvalue equation, in particular in these A and B matrices, which can then be solved to get neutral excitation energies. Oops, one way. So for molecular systems, we have both this full BSE equation implemented, as well as so-called Tandankov approximation, where this B matrix is neglected. And this the implementation is described in this paper here from Chiu in Bogdan's group. We also recently have a periodic BSE implemented for just the Tandankov approximation, which is described in this 2025 paper by Ryu Zhu. And here you can see a comparison of the absorption spectrum of magnesium oxide relative to two other codes. So the BSE is also part of the GW tutorial, but won't actually be covered tomorrow, but just so you know, it's in the same place as the GW tutorial. Linear response TDDFT. This is actually quite similar to BSE. So we have so-called Cassidy equation, where this matrix C resembles essentially the same as this A and B matrix that I showed on the previous slide for BSE. The difference is, rather than GW calculation, you feed into it an exchange correlation kernel. And this is just available for non-periodic systems at the moment with an LDA exchange correlation kernel. And this implementation was also described in this 2020 paper, which had the BSE implementation. And this is mainly work by Jan Kloppenberg and Heiko Abel. And a tutorial for this also appears in the GW tutorial, but again, won't be covered tomorrow as the focus will just be on GW. We also have real-time TDDFT, where here we're solving the time-dependent Kohn-Sham equation to get essentially electron dynamics properties. And a common thing to calculate, as shown in this figure from this nice real-time TDDFT review, is the time dependence of the dipole moment, which can be used to calculate absorption spectra. And this was implemented by Joska Hekele in his PhD work in Peter Kratz's group. And here you see an absorption spectrum of a K-edge absorption spectrum of water with the FHI-aims results in red and green relative to reference calculation and experimental results. And there is also a tutorial available for real-time TDDFT, which shows how to use it both for molecular systems in the example of the tutorial, the absorption spectrum of water, as well as periodic systems. And you can also do Ehrenfest dynamics on top of real-time TDDFT to get non-adiabatic effects simulated as well. So next, delta SCF. So the idea behind this is that you would do an SCF, for example, DFT calculation of a system with a complete full complement of electrons. And then in this example here, you would remove an electron and do another SCF calculation, in this case a 1s electron. And the difference between two energies gives you an ionization energy for the 1s electron. You can also rather move an electron from this occupied level to an unoccupied level, and then you can get neutral excitations as well. And this table here shows that the keywords that are responsible for this in FHI-aims. So there's actually two different choices you can make, either the delta SCF projector or delta SCF basis. And this table shows the availability of the two keywords. And delta SCF projector, you at the first SCF step constrain an eigenstate to have a particular occupation, and thereafter the same eigenstate is kept with the same occupation. And in the delta SCF basis, rather a particular basis function is specified to have a particular occupation. And this is quite useful for example, deep core levels where the eigenstate has essentially contribution from just one basis function. So really, depending on the system you're interested in studying, you choose one or the other of these keywords. And this is mainly implementation work from Rainy Mauer's group, as well as Matthias Kapp. And there is also a tutorial for delta SCF available. And this shows how to use the method with both molecular and periodic calculations as well to simulate X-ray photoelectron spectroscopy. And the final method that I just want to briefly mention is the equation of motion coupled cluster. So this interfaces to Andreas Grunay's code, coupled cluster for solids, CC4S, via an interface CC-aims. So the idea is FHI-aims would perform a Hartree-Fock calculation from which CC-aims would get eigenenergies, eigenstates, Ri coefficients, and a Coulomb matrix, which is converted into a so-called Coulomb vertex, which is then passed to CC4S to do either these ground state methods, so CCSD, for example, or, as relevant to this talk, the excited state equation of motion coupled cluster. And this can be used for both molecular applications, so for example, this ionization potential of the 5 nuclear bases, or for periodic systems. In this example, an extrapolation of the band gap of hexagonal boron nitride. And a tutorial is also available on this, and I should say all of this work is the PhD work of Olga Molman, and you can read more about it in these references down here, as well as chapter 4.1 of the roadmap paper. So with that, I think I am out of time. So yeah, thank you very much for your attention, and I'm happy to receive questions now.
Thank you, James, for this very nice talk, this nice introduction into what FHI-aims can do with excited states. And as James mentioned, the Q&A is now open. So if you look into your Zoom toolbar, you will see a Q&A button where you can ask questions, and then we'll redirect these questions to James and try to answer as many of them as we can. If you are watching on YouTube or on Kushare, you also have the possibility to simply ask the questions via those interfaces, and we are also able to see them and ask them in this session here. So please go ahead and type your questions for James in general to this talk. I don't see any yet, but people may still be typing.
I think if we want to say out loud your questions, you can put your hand up, and I think we can unmute you as well.
That's also an option, yes. If you would rather speak directly, you can also raise your hand and we can give you the option to speak. There's a question in the chat. Can you clarify the difference between the two delta SCF options?
Yes, so the delta SCF projector option applies just to a particular eigenstate. So this eigenstate could have many different basis functions that contribute to it. And so the occupation will apply to this state composed of many different basis functions. So will be useful for states that have some contribution from lots of basis functions. The delta SCF basis just applies to a single basis function. So for example, a basis function that corresponds to a 1s orbital. So this is very useful for core states, which just have an eigenstate, which is comprised essentially of one basis function. And yeah, other than that, there are different availabilities of these two methods. So this delta SCF basis can only be used for molecular systems at the moment, whereas the projector can be used for periodic systems as well. Yeah, so those are the main differences between the two.
Thank you, James. I hope that answers the question. Otherwise, feel free to ask a follow-up, of course.
Yeah, I think both of the keywords are covered in this tutorial as well. So for actual examples of these being used.
I mean, one could also add that most of what was discussed is also described in this roadmap. So there are these different chapters in the roadmap. And so if you want to go deeper and also get the original references, which had been on the slides as well, you also find this in the roadmap.
Yes. Thank you, Matthias. That's correct. And the roadmap can be found on archive. Maybe we can also post it again in our chat box.
Mm-hmm.
Any other questions on this part? There's a question from Hyung-Yong Kim. Can delta SAF be used in excited state calculations?
Yes, I mean, delta SCF is used to essentially compute excited state energies and can be used in either the charged excitations case or the neutral excitations case. So, for example, in this case, in this example here, just an electron, this SCF calculation, this second one, was computed with just an electron removed. So this would be for the computation of, say, this ionization energy of S level. So this is a charged excitation. But we could also, rather than removing this electron, just put it in a valence state instead. And so then you would get an absorption energy or neutral excitation.
Yeah. Thanks,
And
James.
I still would add to that this is one choice and a cheap choice, but the better choice is what really Dorothea will discuss in the next talk. Right?
Yes. Then we have another question. And the question is, how are the numeric radial basis functions UI calculated?
Okay, yeah. So we have different options for these. So there's hydrogenic functions or ionic functions, and they're essentially tabulated based on the orbitals that they correspond to. Maybe Volker can chime in with more of the exact details.
Yes, can do. But in short, they're calculated as radial functions from a numerical solver for spherical potentials. So for example, a free atom potential for the minimal basis, but the free atom will be spherical, so the electron occupations will be chosen such that the atom is spherical. And this is essentially what Hartree, in a way, already introduced in the 1927s, although this has advanced in terms of what it does numerically and stability and so on. But these solvers are very well established. And so that's how we calculate the atomic solutions, also the hydrogen-like solutions, also ionic basis functions. Additionally, we can calculate, of course, Gaussian basis functions as Slater-type orbitals, and those are just tabulated from their analytic formula. So Gaussians are Slater-type orbitals which exist because we do reference back to those methods, are just calculated analytically.
Thank you, Volker, for the added details. So hope that also answers this question. Okay, we still have time for one last. Okay, there's another one. In the delta SCF approach, to calculate the binding energy with the difference of total energies, are the separations of the levels kept the same? For instance, if the order of the levels is changed after the SCF, the resulted excited state won't be the one we want to observe.
Yes, so the delta SCF projector method has this maximum overlap method implemented in it. So the idea is that the state that you choose at SCF step 1, even if it changes order later in the SCF, it still is kept as being the one you want to fix the occupation of later in the SCF. So essentially the idea is you need to know, or you would say do a full SCF calculation and you know the state you want at the end, and then you kind of try and work out what state it is at the first SCF step. And even if they're different, you would just choose the state in the first SCF step, and this maximum overlap method should keep it the same to the end.
All right. Thank you, James. So otherwise, I don't see any questions via Q-Share or YouTube at the moment. You're still, of course, open to ask questions. We can still type them also in the chat. But in the interest of time, I would then transition to Dorothea's talk. But thanks again, James, for your nice introduction and also the answering of the questions we already received. And I would then hand over to Dorothea, who will give a nice overview of all the GW details within FHI-aims. So Dorothea, please go ahead. Feel free to share your screen.
Okay, I hope you can see my screen now.
Yes, screen is visible, so you can start. Thank you.
Okay, so yeah, this talk will focus, as already said in the introduction, on the GW method. And yeah, what will be the content? So first a bit, what type of spectroscopy are we looking at? And then also touching on the questions that were now part of this Q&A. What are actually the limits of DFT-based methods, and then going a bit deeper in GW. And then also repeating a little bit what is the functionality that we have here. Okay, so what is this lecture about? So there will be a little bit of GW theory, so the basic idea and formalism. For more, I just point out there will be also more on GW theory and lectures than in the hands-on workshop in November in Shanghai. And the other thing I want to also focus rather on this talk a little bit the practicalities of GW, so how to obtain well-converged GW results. And I also want to say it again, there's an overview in sections 4.2 to 4.4 in the roadmap, right? So I have a lot of references also in this talk, but if you want to look them up again, so this is certainly also a good reference for that. Okay. So what is theoretical photoemission spectroscopy? And I just want to clarify again, what is actually the types of spectroscopy that I want to discuss here. So it's for, so it's photoemission spectroscopy, inverse photoemission spectroscopy, and what I just want to touch at, so actually not really explain, that would be absorption spectroscopy. So in photoemission spectroscopy, we irradiate our sample with light with a certain frequency nu. And in this process, an electron from a formerly occupied state is removed from the sample. So it's promoted above the vacuum level, which is here indicated by the dashed line. We can also have the inverse process where we have an electron with a certain kinetic energy. And this undergoes then an irradiative transition to an unoccupied state and thereby emitting light, also with the energy here, h times nu. We call this charge excitation because here the system is then charged positively and here negatively afterwards. So this is the type of spectroscopy we can describe with GW. So the other case, when we have the absorption process, so when like an electron is promoted from an occupied state to an unoccupied one, so we form here an exciton, so a bound electron hole pair. So this is not the type that we can describe with GW, but there, for that we have to go beyond GW and solve the Bezier-Salpeter equation BSE on top, or as an alternative approach, use time-dependent DFT. Just to make the distinction clear, so GW can only describe these processes, photoemission and inverse photoemission, so charged excitations. To go a little bit more in detail in the photoemission spectroscopy, we can get the ionization potential, IP, for a certain state S. It could be, for example, the HOMO of the molecule, by measuring the kinetic energy of the ejected electron. We know the frequency of the light that we were using, or that we kind of like were shining on the material or the molecule. For a molecule, the reference is the vacuum level. So if you just take the difference between these two terms, we would have already the ionization potential. For materials, the reference is the Fermi level. So we also have to subtract the work function. So that's the definition of or that's how we get the ionization potential. So the ionization potential is then the negative of the electron removal energies. So how are they defined? So this is here the total energy of the ground state with n electron, and this energy here denotes the energy of the system with n-1. So I have an electron removed from the state S, and the difference between these energies is then the electron removal energies. This defines the electron removal amplitudes. So we will look into them later, just also to have them here on the slide. What is NCAT? So that's the many-body ground state. And this is the annihilation operator that removes an electron from that many-body ground state. So you can write this down in a similar fashion, in an analogous fashion for the electron affinities. So for like the inverse process, inverse photoemission, I refer you here to this this review. If you also want to have a look at this, so in the interest of time, I will go on here to show some examples. Let's say, how does it look like, such a photoemission experiment in the case of molecules? We have here pyridine. In black, we have the experiment. You see here at around 9.5, the first peak, and I try to indicate this. This is from the electron binding energies, basically, of the HOMO and HOMO -1. Here indicated with like the blue and red line. And the next peak basically belongs to the HOMO -2. I calculated here the discrete quasiparticle energies, broadened them to basically get a better resemblance to experiment. So that's what you can basically compute. So such ionization spectra. You can also then compute electron affinities, get fundamental HOMO-LUMO gaps as the difference between the ionization potential of the HOMO and the electron affinity, which are important parameters, for example, for organic semiconductor molecules, etc. Much more common, honestly, for photoemission spectroscopy is so-called angle-resolved photoemission spectroscopy, ARPAS. So for a material, the spectra are angle dependent with respect to the crystallographic axis of the material. So these are here indicated by A. This direction dependence is indicated by a wave vector K. So with a certain angle configuration, you would, for example, get such a spectrum. Now we can vary the angle and get different spectra, and this is basically shown here. So there's basically many spectra with different K vectors stacked behind each other. So each of these different lines is basically recorded at a different angle. Well, this is usually not how you notice this figure. So usually we plot along like a certain angle dependence, or then a certain special points in the Brillouin zone, which gives this probably more familiar plot of band structures. Shown here is for zinc oxide, only here the occupied states, basically converting this figure into this representation. We have the experiment here in white and purple, and the computed bands are basically these red ones from GW. So what you get from these experiments are band gaps, band structures, density of states, band parameters like band velocity, lifetimes, etc. So far to the experiment, and the question is, what could we do with DFT, and what are the limitations? So the easiest idea would be to just use cone-charm DFT eigenvalues and then relate the negative of these cone-charm eigenvalues simply to the ionization potentials for a certain level n. I have here an example for the benzene molecule computed here with the PBE0 function, also already hybrid. You see that the difference on average for these first valence states is 2.2. It's already quite high, so it's usually around 2 to 3 eV. It gets like larger in absolute values if you go to deeper states. So for deep core states, it's already around like 30 eV for like the second row elements. We get 2 small gaps, and already here an indication that with GW we get much closer to experiment. Now for the solids, it's very similar. We have here the silicon band structure computed, basically here the DFT eigenvalues with an LDA functional. We have here the experimental gap of indicated with this green dashed line. You see is much too small. If you take the eigenvalues from Haag to Fock, you see that you drastically overestimate the band gap. And again, here, much better with GW. To give a bit more statistics, we have here band gaps from different semiconductors and insulators. We have the theoretical values on the left, and on the x-axis, the experimental one. So the perfect agreement would be if they all are on the blue dashed line. We are pretty off with PBE, while with here these different GW flavors, which I will explain a bit more later, we are pretty much on these blue dashed lines, so a very good agreement. A better method than using eigenvalues was already mentioned now before, and there were a lot of questions, so I hope some questions are a bit even more answered in detail with this slide. So it's the delta self-consistent field method, so you won't get easily like the deeper valence states, right? So the other parts of the band structures, but it could be an approach to get better band gaps for example, or ionization potentials for the HOMO4 molecule, or electron affinities also for the molecule, then the FT eigenvalues. So what's the idea? So you perform two calculations, as already mentioned. One to get the total energy for the ground state with n electrons, a second one where you moved an electron, for example, from a 1s state, or also from the HOMO, and calculate the difference. To get that one for the electron affinities is similar. But here for the second calculation, we basically add an electron to the system. So that's the n+1 system. Calculating the difference gives us the electron affinity. So that works actually very well for small molecules. If you go to larger conjugated structures, you already see it's much more difficult to often constrain like the hole, even if it's a core electron, so it gets more difficult. I don't say impossible. And also the accuracy then deteriorates. Generally for periodic system, we have the problem that periodic binary conditions and n-1 calculation are obviously a problem. So you have to keep a charge neutral supercell, and you achieve that either by adding a background charge or by artificially adding an electron to the system, which creates artificial exciton binding energies in the system, or different artifacts simply. So it's possible, but potentially inaccurate. And another point is you can have many body effects in your spectra. So not only having the main peak here, but for example, also a satellite. Okay, so now let's go to GW. And I just can cover like the theory very briefly here. I want to refer you here to this review article, which we wrote in 2019 together with my supervisor at this time, Patrick Rinke, and also my colleague, Mark Dvorak. We try to focus there also on the practical aspects, numerical techniques, etc. And to show this equation again, how are the electron removal energy defined? So basically, as energy, total energy of the n electron system minus the energy of the system where one electron has been removed from state S. Similar for the electron addition energies, but here we have like the system where we added added an electron in state S. Now we have like also these electron, like these transition amplitudes defined in terms of like these annihilation operator, so which kind of removes an electron from the system, or for the addition process that adds an electron to the system and acts here on the many-body ground state NCAT. So central to GW is the Green's function, as said before. So it's a propagator, and you see if I write down this propagator in this form, you can actually see the process basically directly happening. Let me explain a bit. We have like this is a spatial coordinate, x, y, z. We have a second one, r prime, and then also 2 times t and t prime, and sigma is here simply the spin. So you can see what this propagator is basically doing. So we have here the time ordering operator, and what it is doing is that it simply puts the earlier time to the left. So if p prime is earlier than t, this operator will go first and act first on the ground state. So what is this doing? So we have here the creation operator. So basically it creates an additional electron. So that's the electron inverse photoemission process. It propagates through the system, is later annihilated at time t at the spatial point r. So if the times are reversed, you see it also allows for the second process. Then the time ordering operator puts this, puts the annihilation operator first, and then we basically first delete the electron. So this is, I think, shows very clearly that we define basically directly this process by defining the single particle Green's function like this. And to now make contact to experiment, we make a Fourier transform and go from the time domain to the frequency domain. Let's have a closer look here. So this is the Heaviside step function, which becomes 0 for negative arguments. So basically, this is the electron removal branch. And this term will get 0. So basically, meaning if I want to compute like the energy, removal energy of an occupied state, so we have only this term. If I have the one for an unoccupied one, we have only that term. So in this way, also the time ordering is kept in some sense, or is directly kept. So now interesting, what you can see here in, let's look at the denominator. Let's say like this. So we have here eta, which is a small infinitesimal. And you see that the poles of this function correspond to these excitation energies epsilon s. So that means if omega equals epsilon s, we divide by 0. So that's a pole, a so-called singularity. And so we directly have the excitation energies defined in the method, which is not the case basically in DFT, just as a hint. So now, when we apply now the so-called Kramers-Kronig relationship, we know when we have a pole in the real part of the quantity, and our quantity here is G, we have like a peak in the imaginary part. And if we want to calculate rather a spectrum, it makes sense to take now the imaginary part of G because of Kramers-Kronig, right? So if I have a pole in G, I have like a peak in the real part, I have like a peak in the imaginary part. And this spectral function is basically the one that we could directly connect to experiment, so the true photocurrent that you actually measure in a photoemission experiment. So now let's have the next look. So if you would have like non-interacting electrons, that would mean I would act, for example, with the annihilation operator on a single determinant, because our ground state is defined by a single Slater determinant, meaning that if I remove an electron from state S, I create exactly one excited state, exactly one excited state Slater determinant, meaning I get simply here, a sharp peak, nothing else. However, if I go to interacting systems, I have not my ground state is not described by a single Slater determinant, but by many. So I have a reference determinant, then adding all like the singly occupied, doubly occupied, triply occupied determinants, and our annihilation operator, for example, is acting on all of them, giving in the end like a bunch of, let's say, electron removal energies, basically the contributions from all the different determinants, which is basically shown here. And when those merge together in one broad peak, then this is what we call the quasiparticle. This peak has like a certain width, so it's also connected with a certain lifetime. So now I was coming with the definition of the quasiparticle peak rather through an explanation that maybe makes sense to people that are very familiar with full CI. I'm also trying to do a more intuitive explanation shown here on this picture. Let's say, imagine you have like an electron ejected during the process, then the other electrons come and rush to screen like the bare hole. And then this composite object of electron, which is interacting with its polarization cloud, the electron is basically moving through the system. Doesn't need always to be like the same electrons around it, but from far it looks like a hole together with like its polarization cloud is traveling basically through the medium. And that's this whole composite object. This is the quasiparticle, which has properties such as dispersion, lifetime, a weight, a satellite spectra, etc. So what's now the basic idea of GW? So an analogy to DFT, we replace the exchange correlation potential by a self-energy, and the self-energy is the energy the quasiparticle feels due to its own presence. A little bit hand-wavy, but I think that's the best we can do in this time. So G stands here for the Green's function and W for the screen-Coulomb interaction. So it's not a name of a person, but rather it's basically the matrix notation we typically use for these properties. The most common flavor is a so-called single shot G0 W0. How it works is that I take my Kohn-Sham energies for state S, and then at the correction term, which contains this self-energy. And this is what we call quasiparticle equation. So exactly this expression is the one. Okay, and to explain the procedure in short, so we first run a DFT calculation to get our Kohn-Sham orbitals, epsilon ks, and the corresponding orbitals, phi ks. From those, we build G0 and W0. We calculate then the self-energy from G0 and W0, and then solve this equation. So let's have a bit closer look. As I said, first the Kohn-Sham DFT calculation. Then we calculate the Green's function, where we have like the orbitals in the nominator, and here the energies enter the denominator. We then construct from G0 the polarizability as product of basically two G0s. Then we compute a dielectric function, and what enters here is this chi0 together with the Baire-Coulomb interaction. So Baire-Coulomb interaction is 1 over r minus r prime. And once we have the dielectric function, we can get the screen-Coulomb interaction by multiplying its inverse with the Baire-Coulomb interaction and then taking the integral. Okay, so we can then construct the GW energy as I have written before by solving this frequency integrals over G0 and W0. So this would be the full quasi-particle equation. What I had on the previous slide was already an approximation. So this would be our quasi-particle wave functions. We make now the approximation that we insert instead the Kohn-Charm orbitals, and then basically integrate also from the left and then get this following expression. So we usually separate the self-energy in the correlation part and the exchange part, and then subtract the exchange correlation functional from DFT. As you can see, the right-hand side already depends on the solution, on the GW energies, on the quasi-particle energies. That means we have to solve it iteratively. We can start here with a guess, for example, the Kohn-Charm DFT energies, and then get the solution, update, insert again, etc., until we solve this fixed point equation. So this is the standard approach, doing this iteration of the quasi-particle equation. You can also do a so-called linearization of this approach. A Z-shot approach is, by the way, also implemented in AIMS, but I would not recommend it. Other ways to get a quasi-particle solution is graphically, or to calculate the complete spectral function. And this is sometimes necessary to understand if you got a unique solution. So that's why I want to mention it. For the graphical solution, what's the procedure? So you calculate the self-energy matrix element for a certain state S on a fine grid, frequency grid. You typically plot like the real part of the self-energy. This is shown here for the HOMO of a water molecule, plotted in the range from -30 to 0 eV. You see have a quantity with a lot of structure. So these are actually poles, so like where you basically have a divide somewhere by 0 in sigma, so it's a singularity. I just broadened it so that you can see something in this plot. And then you try to find the intersection with like this straight line here. And this is plotted in red, and you see the intersection here. The first one is this dashed line. So now you see have also other ones over here. What's to consider is the spectral weight, and you see that we take here the derivative and then the inverse of it, meaning if the Z value is large, then you have a lot of spectral weight. And this is basically here the main solution. We are like the line is flat, so the Z value will be very large. So the larger the better, or is will then close to 1, and this will give like a very small value for Z. So this has low spectral weight. This is rather corresponding to a satellite feature. So sometimes it's necessary to look into this to see if you have a unique solution. So now the most accurate way to get actually the solution is to calculate a full spectral function, which is really expensive typically. You see here that you include also the imaginary part of the self-energy and not only the real part. And as you can see here before, I talked a bit about the spectral weight. So it's maybe not so obvious. If you have looked at self-energies before, you directly see it. But if you plot the spectral function, it becomes very obvious. So here at around minus 12 eV, as shown here, we have indeed our main peak. We have a very sharp peak, which carries clearly the largest spectral weight. And then we had like intersection a bit further. So you see this is very small spectral weight. These are what we would call a satellite in the method. Okay, so an important point is not only how to solve it, but also the frequency integration, as James already mentioned. So how to solve this frequency integral, and the issue is that both quantities G and W have poles, so we can't do a straightforward numerical integration here. However, there are a bunch of tricks, and what we implemented in AIMS is the analytic continuation, which I abbreviate as AC, which is suitable for valence states and gaps, has an n to the power of 4 scaling. The contour deformation is more accurate, is suitable basically for all states, including deep core states, scales N4 for valence states, N5 for core levels. Yeah, much more accurate, but also much more expensive. Let me quickly explain what's the idea behind it. So the idea is that the self-energy has a smoother structure for imaginary frequencies compared to real ones. You see here for the real ones has a lot of structure. And the idea is to calculate, have a set of reference frequencies, let's say 200 imaginary frequencies, calculate the self-energy for each of this frequency, and then basically perform a fit to some analytic model which has poles. For example, the two-pole model, we don't know these coefficients A and B, so we basically get them by fitting to this reference values. And then there's basically a theorem that says if you know the quantity on the imaginary axis, you also know it on the real one. So you basically then for real frequencies use the same coefficients and just insert your real frequency. You can have more elaborate models, for example, the Pade model, which has more parameters, A and B here. And then it's also more accurate, as you can see here. We have this is for benzene, the self-energy. The solution here are roughly at 9 point something EV. The exact solution in blue is contour deformation, and we have the Pade model in green. You see it captures some of the poles here, some of the pole features, averages nicely to the more straighter part of the self-energy. It doesn't capture everything, okay. But the two-pole model, you see it fails to capture these poles also here, but it manages, at least in this case, to somehow average to the self-energy structure. And for more details, please read this paper. So the contour deformation, the idea is to now move the problem to the complex plane. We define the contour integral in this very specific way. So in this is the green shape is the contour integral. Basically, this part has four parts, the one along the real frequency axis, along the imaginary frequency axis, so this term, and then two parts going here around these arcs. You can show that these two terms get zero. And we want to have like this term, right? The self-energy along the real frequency axis. So we simply have to subtract the imaginary term here from the path integral. You can read more about the implementation, for example, in this paper. So that was the frequency integration. It's an important point in GW. Next one is basis set convergence. It's usually slow as for all correlated methods, be it MP2, RPA, cup cluster, etc. I show this here again for the benzene molecule, for the HOMO level. I plotted basically this HOMO ionization potential dependent on the number of basis function or inverse of the number of basis functions. So we have here Gaussian basis sets from triple zeta quality, so quite small, to 6-tuple quality. And you see that even for the largest basis sets, we are not quite there. So we have to extrapolate. And please note, for the smaller basis sets, you might be still like 0.3 to 0.4 EV from the actual results. Now with AIMS, we have also for certain use cases also the possibility to, or for solids in general, to use different combinations, for example, using a tier 2 NaO as basis and then add very specific functions on top to accelerate such convergences. Next point, the starting point dependence is very pronounced in G naught W, not shown here for the water molecule and the HOMO energy. So we usually underestimate the ionization potential with an underlying PBE functional. With Hartree-Fock, we would overestimate. So there's a sweet point usually when you use a functional with 20 to 30% of exact exchange. Then you basically is a experience closest to experiment for molecules, right? So this is for molecules shown here. To reduce the starting point dependence, there are different self-consistent schemes and aims. So the purest approach is fully self-consistent GW sketched here. So you really iterate, you basically solve the Dyson equation as shown here, starting with a guess for G is usually G0, and then calculate chi W and sigma the full way. So this is very expensive. It's only feasible for small molecules, maybe 10 or maximum, maybe 20 atoms. The approximations to the self-consistency, you can only iterate eigenvalues in G. So if you remember, there's, for example, in G, in the denominator, we have the Concham eigenvalues. You could then replace them by your quasiparticle energies and do this over and over again until you achieve convergence. that would be EV-GW not. You can also iterate the eigenvalues in W, so that was not on the slides, but if you look then in the implementation, you see that they also occur there. So you could also replace the eigenvalues in W. Is my personal opinion, I would not recommend it because this often leads to under-screening. For the fully self-consistent GW, so this is in this paper, by the way. Okay. Now, finally, I want to close with a few practical guidelines. The points that you should consider when running GW is what frequency integration technique to choose, your basis set choice, convergence, the starting point dependence, or the choice of a partially self-consistent scheme. And there are also other convergence parameters, for example, the number of frequency points you use to, for example, in the Pade model, right, as a reference frequencies, etc., and how many Pade parameters you choose. So going to molecular valence states, generally analytic continuation works well enough. So I would use a Pade model if it's numerically stable and if it's available. You have to check convergence with respect to the number of Pade parameters. Usually there's a guideline of 16 is usually good, but also with respect to the frequency points. PB0 is usually good for molecules, right? So I say explicitly for molecules, but you might also try a self-consistent scheme, is typically affordable. So you can, for extrapolation, you can use a Dunning basis set, but this is just one, right? So you can also use different one like NAO optimized ones. For molecular core states, contour deformation should be used, as I said earlier. So deep core states here with binding energies larger than 100 eV. You should definitely use some self-consistency in G to get a unique solution. So that's actually very important. All the schemes listed here work well. So this, what I call heading shift, is an approximation to EV-GW not, basically stopping at the first iteration step of EV-GW not if you want. Compared to experiment here in the table for the core 65 benchmark set, they perform all very similarly for absolute binding energies of 1s states. You need relativistic corrections, of course, and you also need either a basis set extrapolation or, as I said, sometimes we can also design very specific basis sets to accelerate the convergence. We found that practically also tier 2 and then adding Slater type functions, so STOs, works also pretty well. Now for the periodic solids, it's the same story. So you have to check how many frequency points you use. Auxiliary basis set is also here an important point, convergence with K points anyway. And also basis set, of course. So here an extrapolation with correlation consistent Gaussians wouldn't be feasible or also not in any case practical. So what we do here is usually using also a tier 2 NAO as basis and then add STOs. This is zirconium dioxide, and you see also here, if you progressively add more STOs, how you then basically start to converge the calculation. And as already mentioned, this is the implementation paper here from 2021. To summarize quickly the functionality, so we have single shot G0 W naught for molecular valence states, molecular core states, periodic systems, eigenvalue self-consistency, for all the molecular cases, fully self-consistency also only for the molecular cases, but it's also terribly expensive. I think is not really feasible. Just to mention it briefly, even so that was not part of the talk, we have there's also BSE performed on top of GW, possible for molecular core and valence states, and also periodic systems now. Vertex corrections, a bunch, cumulants, this is basically related to getting correct satellites. And other ones that are more sophisticated ones. But again, this is typically also expensive, at least the other two ones, and molecules only at this point. And I want to close now with a list of the literature summary. So I didn't put everything, I just picked what I consider the most important implementation paper for each of or first benchmark of the method, all of these flavors of GW implemented in AIMS. And then I know it's not today, but happy computing tomorrow. And now I'm looking forward to your questions.
Thank you, Dorothea, for the nice presentation and all the overview of what is implemented within FHI-aims. And as before, the Q&A session is again open. You can use the Q&A button to ask your questions, or also on YouTube Q-Share, or feel free to raise your hand to speak. And we already have a first question from Samuel Ponce. Many thanks for the presentation. On slide 26, could you elaborate on the O(5) scaling of contour
yeah.
deformation for the core states?
Yes, it's not directly visible from the slide, so I didn't put that much technical details, but I can nevertheless try to explain quickly. 25, right? So if you have the contour deformation, maybe this is better on this slide, you will see that that this term scales n to the 4, so that's the integral along the imaginary frequency axis. But this term is basically obtained by applying the residue theorem. So meaning that you end up with like a sum over occupied states, basically then times occupation factors times W, where the argument is epsilon minus omega times the Heaviside step function. And then you will see that for core levels, you will sum over the whole occupied states. And then W scales n to the power of 4. You have like a sum over occupied states in front of it, and then suddenly you have your n5. I mean, I would have to write down exactly the equations, but it's basically this term that is screwing you over, like which comes from this path integral. And to explain, like for valence states, you have only very few residues, right? So you have to then you keep basically the W scaling because you don't sum over all occupied states, but only 1, 2, or 3 contributions.
Thank you, Dorothea. Thank you, Samuel, for the question. Any additional questions? Maybe just a quick question for me. Could you comment on the limitations of the different approaches with respect to system size? So what's currently possible for example, the periodic GW part and also the molecular ones, maybe the biggest test cases you already ran?
Well, with the M4, like this one for the molecular case, yeah, I think like 250 is okay. So I mean, need a couple of cores. And I think as James had a figure on this in his slides where he had like 80 zirconium or 81. No, yeah, it's around that. I don't know how much exactly. I think it was something between 80 and 90 in the system there for periodic systems. But I think that was then 20,000 cores, right? And yeah, fully self-consistent GW, I would say that's rather maybe 10 to 20 atoms really feasible to take there. The eigenvalue of self-consistency is typically not adding too much. It's more like, yeah, you run maybe a factor 10 or something more, right? And yeah, I mean, the BSE it depends a bit what you do, right? So for molecules, typically GW is the more expensive step. And the BSE is then faster. For periodic system, I would not, yeah, might be more, depending how big your K-grid then is, right, for the BSE step. That I can't clearly say, but for the vertex corrections, the cumulant is not costing much on top, so there's a miracle of the cumulant, but also are very expensive, right? So then it's more like a few, I don't know, 10 atoms, 20 atoms with like these vertex corrections.
Thank you, Dorothea. There's another question about the convergence with respect to the imaginary frequency points when using the analytical continuation. Usually, how many points do you need to be converged, and which kind of grids can be used within FHI-aims?
So grids, the standard is the modified Gauss-Legendre grid. And so it depends if you really want benchmark quality. I would say like 100 grid points is a very safe setting. So you probably can try even less, like maybe 60, but I would say 100 is very safe. It's a good setting. I mean, if you really want to run a benchmark of small molecules, you can also use 200. It depends also a little bit on, let's say, typically if you use a pattern model with 16 parameters, you definitely have to, I mean, you have use at least 16 frequency if your part model has like 16 parameters, right? So, but it's better to use more because you also have to, they enter in the second part where you do a numerical integral in the technical implementation. So I would generally like say, please use more than 16 frequency parameters. But let's say if you have 128 part parameters, you need at least 128 frequencies, right? So it's also a question if you see you have to, your self-energy has a lot of structure and you need to use 128 parameters, then also you have to use 200 frequency points. But general is 16 parameters, 100 frequency points is usually really safe.
All right, thank you. I hope that answers the question. Then there's another question. Is self-consistent GW usually accurate with in combination with BSE for neutral excitations, or does it depend on the type of system or whether it's a periodic or molecular system? What is the general guideline in choosing GW flavors with different types of molecules?
I think there were several questions at once.
Yeah, I think there are probably two different ones, but yeah. So the first one is self-consistent GW. Is it accurate with BSE for neutral excitations, or does it depend on the type of molecular system?
I think for fully self-consistent GW is not implemented in together with BSE, with neutral excitation. So you only get like charge neutral excitations from it, right? So only the photoemission experiment, and it's also not implemented in combination with BSE, as far as I know. Because the output is a bit different. You don't get like, with the other ones, you really solve like the quasiparticle equation and get discrete quasiparticle energies. When you run fully self-consistent GW, you get like a whole spectrum, right? So you really plot the spectral function. And as far as I know, it's not implemented. So you would have to go there and identify where are the peaks to then provide an input for BSE. And as far as I know, is not done. And I think also not very reasonable, I would say. The second question, which GW flavor to choose? So for core states, I would definitely go for something like EV-GW not, or an approximation of it like the heading shift. So that's necessary. Otherwise, you won't get the solution. So not like a bad solution, but no solution at all, because the separation between your main excitation and the satellites is not right. So you have a major charge transfer and a really crazy multi-solution behavior. So you definitely need this to make the theory right. So that's a very strong point. Otherwise, for valence states, there but depends a bit on the system. So as I say, like G0W not at some hybrid functional like PBE zeros already in most cases good, and otherwise I would rather use I would always rather use EV-GW not. So I would usually go for this scheme because according to my opinion, it works for the right reason, right? So here you changed arbitrarily somehow your screening, and this is usually not good. So like you go into the tendency to underscreen. But this is other people will tell you differently. So I would always rather go for this scheme because what is doing something that is basically separating quasiparticles from satellites, and it's doing something in the theory that I understand, and here seems to be arbitrary to increase the screening. But a lot of people like that and tune the starting point underneath. Okay, so I would either tune the starting point or use one of the self-consistency schemes. So my proposal is use EV-GW not at a PBE functional, usually works well, or use G0W not at PBE 0.
All right, thank you, Dorothea. I hope that answers the question. There's another one, and it's on why are the Dunning basis sets typically not recommended for periodic systems?
So, I mean, yeah, the Gaussian basis sets are basically really large. So you get an ill conditioning already in your S step very quickly. That's an issue, right? So if there's Gaussian codes that do, of course, periodic systems like CB2K, but then they have special short range functions so that you don't get into the ill conditioning. But these basis sets are for molecules. So yeah, you would have really not a good chance with bigger molecules even to get through with it. I mean, maybe bigger molecules still, but like solids, definitely not, I would say. Yeah.
Yes, thank you. Then there's another question from Samuel, and could you comment on the validation efforts between GW for periodic solids and FHI-aims and other codes? So for example, Yambo, Abinit, Berkeley GW, and so on, and the stability of the analytical continuation in general. So what is the order of magnitude between the agreements between these different codes?
Yeah. Yeah, I'm smiling a bit how to say this. So there was efforts in that paper, which I actually didn't want to mention too much, but this is another story. So it was a comparison between up-init, exciting, GPOR, and AIMS. These 4 codes where we tested a bunch of solids. And there's a comprehensive benchmarks for molecule, right? The GW100 and a lot of codes put effort and achieved really good results, really pushing it, even different basis sets going in an increment around 50 millieV. So for solids, it was much more difficult, right? So because there's so many different flavors then implemented in the codes, and there was not so much effort yet to make the codes numerically agree. And I think this is still missing in the GW community, to put there more effort to get the same answer with all the codes. But then it's partly it's not even that's not implemented, but rather that converging such things out with really tightly out with the basis sets, that's tricky, that's computationally expensive, and then other codes might not reach the convergence there. So that was our main problem, and then we had to use extrapolation equations, and right. So I mean, such a numerical benchmark, one should afford to really converge out brute force. And if we then say, okay, for some systems we had deviations of 100 millieV or even 200 millieV, that's not very satisfying. But I think it was mostly due to the fact that other codes, the implementation, were not able to converge out. So also the conversion is not same for all systems. Silicon behaves very nicely. You can converge it out very easily and all codes get the same answer. There was no problem, right? So you have more complicated systems like zinc oxide, and then the codes disagree by 0.2 EV. So it's an issue we still, the whole community has to work on. And this is more like an issue of like computational efficiency, as I think it should converge out K-grids to converge out basis sets in particular. And there was another question before, analytic continuation.
Yes,
so,
exactly.
So yeah, 2-pole is usually more stable. So that won't give you arbitrary results whatsoever. But as you see, it's also less accurate because it has just like two parameters, right? It's a 2-pole model, as already the name says. So the Pater model is numerically less stable because it's in the end like a Thiele approximant. You can also say, you see, if you can rewrite this and you see it's like a recursive procedure to get the coefficients, and that makes it numerical a bit unstable. So it's usually my experience for valence state numerically stable enough. So valence states may be up to going from 0 to minus 20 EV. And then it starts to get numerically, how to say, you will run a second time with a different number, of course, and your values start to fluctuate in 10 to the power of minus 3. You deeper you go, the worse it basically gets. But that's why I'm saying for valence states, it's usually fine. Then I would use Pater if available. I mean, 2-pole, as you see here, is not bad, right? So it still averages through it. It's more like if your pole is too close by, then it could happen that you're deviating more. Yeah, and contour deformation is really stable, so there's no issue at all.
Great. Thank you, Dorothea. Hope that answers the question. We have time for probably one more in case there is one. So I'll wait a few seconds for the final question for today in case it comes. Okay, I'm also checking the other channels, but at the moment I don't see any. Okay, so then I think we had already a nice round of discussions and questions. So I would like to thank Dorothea again for your nice talk and also being present for the questions and all the work you put in here. I think this was a very nice overview also, of course, to James, our first speaker, on what we can do within FHI-aims for excited states. So I hope you all enjoyed the presentations today. Before we close, of course, I want to point out that we have the tutorial sessions tomorrow. This was also already mentioned briefly by Dorothea. So if you want to try these things out, and we also do, for example, frequency convergence, so with respect to frequency points, what happens with the different basis sets and so on. So if you really want to get hands-on in trying out the different GW flavors and then seeing how they converge and so on within FHI-aims, please feel free to join our hands-on and discussion sessions tomorrow. So, but with this, I would then close today's webinar. Thank you again, everyone, for being here, for asking all the questions. Thank you again to Dorothea, also to James for the nice presentations, as well as all the discussions from all of you. And with this, I would close the webinar for today. So thank you, everyone, for coming, and then see you next time. Thank you.
Bye.
Bye.